While the conceptual formula for the sum of squares, the simple sum of x minus x bar squared, makes sense and is very clear as to what one is trying to do, computationally, it's pretty cumbersome to actually use, especially if you don't have a computer. You have to add up all of the scores and then divide by n in order to get the mean, and then go back and subtract the mean from each of the scores, and then go back and square each of those values and add them all up. Fortunately, there's a more simple, although less intuitively clear, computational formula that you might see in textbooks and that you can use yourself if you ever need to. This short video walks us through its derivation. We start with the conceptual formula for the sum of squares, the sum of x minus x bar squared. First, let's expand x minus x bar squared and write it out as x minus x bar times x minus x bar. We then further expand this, keeping track of the fact of the summations all along the way. xi times xi is xi squared, summed across everyone. Xi times the negative of the mean for x is also summed across everyone. Because of the minus x bar, it results in minus the sum of x bar times xi. Xi times the mean for x shows up a second time, so we have the sum of 2 times x bar times xi, summed across everyone. Finally, we have minus the mean of x times minus the mean of x, which results in adding the x bar squared values across everyone. Now, let's focus on this expanded equation. In the middle, we see the sum of 2 times x bar times x. 2 times x bar is a constant. It's exactly the same for everyone in the sample. We can therefore factor it out of the summation, and it becomes 2 times the mean of x times the sum of all of the x's across everyone. The same principle applies to the sum of x bar squareds in the final term. The squared value of the sample mean doesn't vary across people. The mean, and hence the squared mean, is the same for everyone. So we can also factor it out of the summation. Notice that in this case, it leaves nothing behind in the summation. In that case, remember, we were still adding up the squared value for the sample mean over and over and over again for each person in the sample. So this becomes n times the sample mean squared. Now, let's take a look at the 2 times x bar in the middle term. Mathematically, what is the mean of x equal to? It's the sum of x divided by n. Let's replace x bar with the sum of x divided by n. We now do the same thing with the n times x bar in the final term, replacing x bar squared with the sum of x divided by n. We can then take that quantity and square it. Returning to the middle term, we now move the sum of x that is outside of the fraction into the numerator, and rewrite this as the sum of x quantity squared. In contrast, we take the squared fraction in the final term and expand it out. Notice that we have an n outside of the fractions and 2 n's, or n times n, in the denominators of the fractions we're multiplying. We can cancel out the n outside of the fractions and one of the n's in the denominators, leaving us with the sum of x times sum of x divided by n. We can rewrite the sum of x times sum of x so that it is the sum of x quantity squared. Now notice the final two terms. Negative 2 times the sum of x quantity squared divided by n plus the sum of x quantities squared divided by n. These can be added together, resulting in minus the sum of x quantities squared divided by n. The final result, sum of x squared minus sum of x quantities squared divided by n, is the computational formula for the sum of squares. It gives you the same answer, but saves a few steps in the calculation process. You may see it from time to time in papers or textbooks, but when you do, just remember, it's just the sum of squares. Thanks, and I hope you found this useful.